Greetings to all. We will be presenting our research project Noma for 5G. The baseline idea of Noma is to serve multiple users using the same resource in terms of time, frequency and space. The available Noma techniques can broadly be divided into two major categories, that is power domain Noma and core domain Noma. In power domain multiplexing, that is the multiplexing that we are using, different users are allocated different power coefficients according to their channel conditions in order to achieve a high system performance. The transmitting side of the Noma uses superposition coding at the transmitter end. The different power levels have been assigned to users using the power coefficients. The receiver side of the Noma uses SIC, that is successive interference cancellation technique, to retrieve data of both the users. To implement the Noma, we are using the SDR. So what is SDR? A software-defined radio system is a radio communication system which uses software for the modulation and demodulation of the radio signals. An SDR performs significant amounts of signal processing in a general purpose computer or a reconfigurable piece of digital electronics. The goal of this design is to produce a radio that can receive and transmit a new form of radio protocol just by running new software. The SDR we are using is YCOM-T.
We'll be demonstrating the YCOM-T. So this is the YCOM-T setup for our project. We are using an IF modulator. An IF modulator has a receiver and a transmitter. We've taken two antennas. One antenna is connected to the receiver and the other to the transmitter. So this equipment is connected to the PC by a USB cable. Now I'll be explaining the demonstration of the program. We initially enter YCOM-T and we get the command window. So here we'll be choosing the experiments and we'll be choosing this folder called QPSK. Now the QPSK folder that we choose has both receiver and transmitters file present in it. So since we are implementing the entire project on IF, IF is chosen. We are setting the frequency offset to 1000, phase offset to 0 and SNR to 100 dB. Let's now generate the transmitted signal. As we can see, this is the transmitted signal. Now in order to see the result, we'll be analyzing the given circuit. So this is the first error curve for LMS convergence. Then we have constellation of filtered points after tracking. We have constellation of filtered points after phase rotation. We have constellation of received signal after coarse frequency correction. We have constellation of filtered point after medium frequency. Finally, we get the constellation of the received signal. So this is the final output. So this is the final output. This is a QPSK modulated constellation of the received signal. Thank you.